Are there any questions for Dr. Prosser or Dr. Pfalzer? Yes.
Anna's still here. Yeah. I can hear you, Scott.
I was wondering if you could give us a little more detail about the ACE tRNA method, level of specificity to that stop codon compared to other stop codons, and how quickly or easy it is to adapt that to alternative variants, different stop codons within that gene.
Yeah. I think this is really the critical question and has been with this approach since its inception. And there may be some folks in the room actually that can speak to it more carefully than I can. So to get to Scott's point, the concern is you overexpress something that can read through stop codons. What happens if it starts reading through canonical stop codons that you need there for a reason, right? And so this has been evaluated by some of the investigators who helped develop these approaches. And there's a surprisingly high specificity for premature stops versus canonical stops. And the general idea is that there's something about a canonical stop codon that makes it much more difficult in that context to read through than a premature stop that wasn't supposed to be there in the first place. I think that's the simplified answer. Now, in terms of how you would change the construct for different stop mutations, so swapping out whether it's an arginine or a glycine or the other amino acid, that would involve just a new plasmid construct. And so this would be a different construct in a capsid for the different stop mutations, but only based on amino acid, not for each individual arginine mutation, if that's clear.
Ben, this is Greg Robinson at Tavard. To give you a little more answer on the canonical stop codon, what happens is that there are release factors tethered to the 3' untranslated region that outcompete any tRNA. So they get put in there and release the polypeptide chain before any other tRNA can get in there. So that's why you get very low read through. In fact, we've seen with ribosome profiling and LCMS that you get well under like 0.05% that's dealt with the cellular physiology.
So glad you're in the room. Thank you.
Okay, Ben. Hi.
Do you want to come up as well? Sorry. Oh, yeah.
It's okay. When you see the upregulation of Syngap with your ASO, the steric blocking ASOs, do you actually, that's total mRNA, right? Do you also look at the different isoforms later on at protein level and RNA level?
So if you're asking about the ASO strategy, do we see distinct upregulation of specific isoforms? And you're referring here to...
Is it like just proportionally upregulated, all the isoforms?
So I don't think we've looked at that closely with that particular approach. We have developed probe sets to be able to detect the different Syngap and C-terminal isoforms, for example. And this is particularly interesting to us in terms of the CRISPR activation strategies, because we have guides that target different promoters, and we're trying to understand which promoter links to which isoform, et cetera. And we actually think it might be cool because we might be able to selectively upregulate certain transcripts over others. With the ASO splice switching strategy targeting the NMD exon, I wouldn't speculate that there would be transcript specificity or isoform specificity, but we haven't proven that.
Okay.
That's wonderful work. I have a bit of an unfair question.
Oh, great.
Yeah, so I understand that. With many of the mechanisms that you proposed for treatment, it seems like as though there's a question about how much you'd have to restore to normal, the gap expression. Has anyone, or have you looked at all whether or not the question is if you had uniform increase in expression versus mosaic increase? Because it seems like with AAV and other vectors, likely we'll only get a certain percentage of normalization. And with these preclinical trials, it seems like as though perhaps it'd be possible to assess this in some way.
I mean, I think it's, of course, a critically important question really for anything that you're trying to upregulate across the brain. We haven't looked at it systematically. For SYNGAP1, it's something we think about a lot with both approaches. I think, with improved capsids, with improved regulatory elements that can drive expression in different ways, we'll start to get to those answers in the next couple of years, but it's still pretty early days, I would say. And in terms of really, again, minimum effective dose of Syngap, minimum brain regions, minimum distribution, to me, I don't have answers to a lot of those questions yet. And I think that that's kind of something I'm really inclined to chat with as many people in this room as I can about. Because that's the amount of upregulation that we see experimentally with certain approaches. For example, we think that we may be capped at that level of upregulation. And so then it's a question of, if we get 50% back to normal, is that enough? Yeah, yeah. For ASO right now, that is the standard, is indeed an intrathecal injection every 3 months or so. We are working with groups, and I guess I don't want to say anything out of turn, but with improved ASO chemistries that may have longer half-lives in the CSF that may be able to reduce that frequency of injections. I think this is something else that we really would love to motivate the field to get better ASO delivery protocols. I think some of the early results of ASOs and NDDs is super exciting, but these kids that have been on 3-year follow-up, getting an injection every 3 months, it's really tough. Right? And so I'm hoping that with improved ASO chemistries, that burden can be substantially reduced.
Maybe not a great question, but something that I have in my head as a parent is, what's the computer simulation ability to actually do simulations of these processes without doing the actual research physically? And are we there yet on that ability to do that? I see things on the internet like the Brian simulator for brain neurological simulations. Those are much more like, that's super high powered computing that's doing that. But are there similar things that are being done on the molecular level?
That's a really hard question to answer concisely. And I think it really depends on the more specific question that you're asking, right? So I covered a lot of different domains here in this brief talk, and certainly a number of them I am not aware of any way that we could simulate or address computationally. But certain things in terms of drug docking on a particular target and how that may influence the molecular structure of said protein, there's a lot more that can be done there. So I don't know if there's an easy way for me to answer that very concisely, but I'm happy to chat more at length after this session.
Okay, thank you.
Thank you all very much.